Alright, so we're going to look at chapters 5 and 6, which is using some of our trig identities, mostly the double and half angle identities, and then we'll get into the law of cosines, law of sines, really focusing on the harder part of that, which is our ambiguous case situation. So for the first example, we're given sine of theta is -4/5, and then where x is between 3 pi over 2 and 2 pi. Well, my notation is pretty poor here in that I have thetas and I have x's, so I'm just going to change them all to x's. And the two things that this lets me know is sine is negative in both quadrants 3 and 4, but x is restricted to the fourth quadrant, which is important because what I'm going to need to do is solve for cosine. So if I look at my right triangle, I know that C has two possible values, so plus or minus 3, but since I'm in the fourth quadrant, cosine is positive, which means that I only have the positive 3 as my answer choice. So cosine of x is 3/5. So that's the hardest part of this. Now I just apply my my identities. Sine of 2x is 2 sine x cosine x. Well, I just figured out what sine of x and cosine of x are. So I plug in -4/5 for sine of x and 3/5 for cosine of x, and then I run through my fraction. I get -24/25. If I was to figure out cosine of 2x, well, that's going to give me my identity that I picked. There's three of them. Is 1 minus 2 sine squared x. And the reason I picked the sine, the one with sine in it, is that I was given a value for sine. So let's say I screwed up my cosine calculation of 3/5. I could still get this right. So I just plug in -4/5 for sine of x. I square it, and I get -7/25. Now I do have an identity for tangent of 2x, but I can just take that as sine of 2x over cosine 2x, take the values I just found, and that gives me 24 over 7. The half angles are a little bit trickier in that I have to evaluate the positive or negative part of this. So I take out the cosine value and I put in 3/5. I evaluate my fraction. I get plus or minus √1/5. Well, if I take half of my angle, so right now that's where x was, and if I take half of it and divide the inequality on everything by 2, I'm given now where the biggest x can be is pi. Well, any angle bigger than 0 and less than pi is going to have a positive sine value, so I get the positive √1/5. Same type of idea for cosine of 2x. I use my identity, then I evaluate the sine and get -√4/5. Tangent of 2x, I use my sine value and my cosine value, and there I go. That would be, I could simplify that from there and get -1/2 as my tangent value. In terms of deriving the law of cosines, we use this very kind of specific case where we have a general triangle. So what's great about the law of cosines, it's for any triangle. So it can be obtuse, acute, scaling. It doesn't have to be a right triangle like the Pythagorean theorem. I have a point. Point B is over A up 0. And I have point A is B cosine theta, B sine theta if I was to draw in my right triangle. So just using the distance formula, I get c squared, or using my, using my distance formula, I get that value and squaring everything. And then it's just algebraic manipulation to go from there, where I factor out a b squared, cosine squared theta, sine squared is 1. That's going to drop out. And I'm going to be left with b squared plus a squared minus 2ab cosine theta, which is my law of cosines. More interestingly is how we use it. So if we were given a triangle, now all of these have side-side angle given, or angle side-side, depending on how you order it, which is a potential ambiguous case. And we'll see that means three different ways here. First off, to solve it with the law of cosines, I'm looking for side C. I only know the angle of 110. And I plug through it, I get a quadratic, and I start to solve that with the quadratic formula. So my quadratic formula, if you remember from algebra, looks like this. I work through it, and I get in my discriminant -925, or about that, which is going to be an imaginary number. I can't have a triangle with an imaginary number, and so I get no solutions here. Nothing will work for this. And if we think about it, that makes sense. The 110 is my biggest angle, have to be my biggest, and 14 is not my biggest side. So this angle B would have to be my biggest angle, but it's not going to work with the 22 here, because I don't have enough degrees to make anything bigger than 110. So geometrically I can think about it, or when I get my discriminant of negative 925, that tells me that I have no possible triangle. Alright, if I look at the next one, geometrically, sorry, just stepping back, so if we really were to try to construct this, this is what would happen. I make my angle of 110, and then if I have, there's my angle, if I put my side lengths of 22, so that's a circle with the radius of 22, and this is a circle with radius 14, we can see there's nowhere this is going to meet. This triangle and this angle is just not geometrically possible for this to work. So lots of different reasons why I can come to the conclusion that there's no possible triangle, but the big idea is that there is no possible triangle. Alright, if I was to set up the next two, you'll notice that again we're going to have this side-side angle situation, and we're going to use the law of sines to deal with this. So if I was to plug through my math and figure out the missing side, so set up the law of sines and then solve for s using an inverse, I have a restricted range for sine inverse, and I'm only going to get from the calculator 56.7. But that's not the only value where I get a sine value of that. So if I was to take, let's see here, my sine, I go straight across, so horizontal line, I will get another sine value over here with a reference angle of 56.7. So to figure out what that really is, I take 180 minus 56.7, I get 123. So now the question is, can a triangle exist with both this angle and 56.7, given that this other angle is 42 degrees? So I just draw a triangle, helps me to visualize it. 42, 123, well, that's less than 180, so this could be 15 there in my triangle. So that works. And then I plug in the 56.7 to my original answer, so I'm going to get that triangle. So there's two triangles that are legitimate. I could find, with the law of sines again, I could find the missing sides for T and S. Oh, sorry, for T on both of these. So that would work. For the next one, we're going to see what happens here. So if I do the same setup, I figure out angle B, and it's 32.5. If I figure out the other angle, so again, looking at the opposite side here, so if this was a 32.5, and then I go across, what's that going to look like? Would be an angle of 147.5. Well, it's pretty obvious that I can't have an angle of 75 degrees and 147. It's going to be bigger than 180 right off the bat. There's no triangle that exists. There's only one solution here. So what we want to take away is that when we have this ambiguous case, we have the three things that can happen: no triangles, two triangles, or one triangle. The last one is a very specific case where we just know all the sides of a triangle, and we want to find the area using Hero's formula. To do that, we have to figure out the semi-perimeter. The semi-perimeter is half of the perimeter, and then we plug that into Hero's formula, which is the square root of the semi-perimeter times the difference of the semi-perimeter and the sides. And we just plug into our math, and we get about 42.4 square units.